time for us to resume, and Kevin Wayne is going to tell us about isoperimetric problems.
Yep. Okay, so today's talk is on isoperimetric problems. And it is split into two sections. The first section will talk about the watch multipliers, and the second section will actually analyze the problems themselves. Now, during the whole talk, I will present two theorems. One theorem here in the first section, and the other one here. Now, the reason that and for each of those theorems, we'll have an example for the example. And to actually prove the theorem in the second section, we'll actually use the first theorem. And of course, we have to look at Didel's problem, or Didel, depends on pronunciation, I suppose, which is the oldest problem in the calculus of variation topic. And it's quite interesting. Okay, so let's start with Lagrange multipliers. Well, what Lagrange multipliers is that it's an optimization technique or method that maximizes a function f under the constraint of a function g. So that's a little bit technical, but we can of course think about a problem like this. So everybody done their vector calculus assignment, right? Because I don't want to tell you the answer for that. Okay. So in a problem, you know that you got surface in space, and what you're trying to find is the maximum or minimum point within a domain. The domain you have is the constraint. The function you're trying to maximize is of course the surface. And we'll actually look at how to solve this problem in Lagrange multipliers. So here's actually the statement of the theorem itself. And the theorem simply says that, well, if you want to optimize f on the constraint of a g of x equal to 0, then you have to solve these two equations simultaneously to find the constraint optimization points. So the first, you can think of these two equations as being criteria for constraint optimals. And the first criteria is not surprising at all, because that's our constraint. You know, you always want to satisfy the constraint. No surprise there. But the second criterion is a little bit not so obvious at first, because what's all the grad and lambda came from. So our main focus for this topic is to understand where does the second criterion actually come from. Task? Yeah. Okay. So the origin of Lagrange multipliers, and especially the second criteria, comes from some geometric intuition. And in particular, we'll look at the contour plots. Now, here I have got contour plots of f, which is in the blue line, and the contour of g, which is in the red line. And by the way, this is the actual assignment itself, but let's don't worry about that equation first. We'll look at the geometric meaning behind that. And we're going to look at some behavior of these plots. And this is just one picture zoomed in. Now, let's suppose, is that right? Yeah, okay. Now, let's suppose there's actually a maximum point. Okay, we only consider maximum point for now. Now, if there's actually a maximum point, then we can make the first observation, which is really obvious, that that point must lie somewhere on G, because you must satisfy G. So on the contour plot, it must lie somewhere on the red line you constraint. Our second observation is really obvious, I would suppose, because, well, just by looking at that, right, you know that G intersects with many different contour lines of F. Okay, there's one, and there's one, and there's one. So our problem of optimization on the constraint is now equivalent in terms of this contour plot is equivalent of saying this. Well, suppose there's the maximum point is here. Then the contour line of f that passes through this point, that value must be a maximum compared to all the other plots that intersected with G. So for example, of this point here, that's 0.75 that intersects with G. For this one, well, this is 0.5, but that also intersects with G, but that will be a little bit higher than that. So we probably suspect something funny is going on here, and this will probably be our maximum. Actually, is there any question about how I come to that equivalence in terms of contour plot? Any question about this part? Good? Okay, good. Okay, so now this is a zoom-in picture of that region I was referring to. And here you can probably have a guess that if there's actually a maximum point, they must intersect tangentially. Now, how do I make that claim? In fact, that's the extraordinary claim. How can you actually make this claim? Well, to justify this claim, you have to use geometric intuition. Now, suppose that you are walking along you're walking along this G. Okay? You're walking along that. Now, as you walk along, you know that the G intersected with you as it's changing its value. But what happens when it intersects tangentially? Well, if they intersect tangentially, the value of f does not change locally. And that corresponds to, in ordinary calculus, if I can find my chalk, it's not here. It's in the box. You know that in ordinary calculus, you have x and f of x. And locally, if you have a maximum around here, as you vary along x, locally, the value for f does not change. And this is basically the same idea. The only difference is that you're walking along G rather than from the x-axis. So that's a claim that if there's an optimization point, the two curves must intersect tangentially. And that's equivalent, definitely equivalent to saying they have parallel tangent vector. And that's, of course, equivalent to saying they have parallel normal vectors. You can think about if they are parallel tangentially, their normal must be parallels. And of course, another word for parallel is the word linear dependent. So, just by this line here, we justify our first criteria. Or, sorry, you're supposed to be second. Anyway, we justify this criteria that, which is why I written here, because normal vector for the contour plot of f is graph f. And it's linear dependent, that's why I have the vector there. Sorry. The constant there, and graph G is definitely the normal vector for the contour plot of G at every point. So, are we any question, or do you want to clarify this in an alternative way? Are you good? Okay, great. Okay, so here's actually the Lagrange multipliers equation itself, and it's nothing more than I just showed you. You have to solve these two equations simultaneously, and once you get a bunch of points there, you will evaluate these points. So, how do we know these things work? Well, it's simple. We do example. So this is actually question 3 in your vector calculus assignment. And this is the function you have. And now I multiply the equation. All right.
Have you hand this on me?
Yeah.
We already get it back.
Return
I think you guys got it right because I don't want to cause any trouble. Otherwise, I just leave out a solution. I'll just cut a solution if you're not happy with it. But the domain, we don't care about what's the interior. Because if you done question, interior is simple. What we really care about is the boundary projected upwards. So that's why we have equality sign rather than the inequality sign, because we only care about the boundary points. And of course, solved by the Lagrange multipliers, and it's definitely saying that we want to optimize f under the constraint of G. So this is time to switch to the visualizer. And let's see. Let me write the equation down first. F of xy equals to x squared plus xy minus x4. G of xy equals to x squared plus y squared minus 1 equals 0. Okay, that's our question. I want to optimize. So firstly, we'll form this. We'll actually calculate the gradient of each functions. So the gradient of the grad f actually equals to 2x plus y minus 4x cubed and x. Grad G is simply 2x. This is tilted a bit. Sorry about that. So what we're going to do now is equate the partial f partial x with the partial g partial with the partial of g. So that's 2x plus y minus 4x cubed equals to some constant lambda. Okay, that's what we have there. Times 2x. And at the same time, we have x and equate that with this. So that's x equals to lambda, 2y. And our third equation, notice that we have x, y, and lambda, so we need 3 equations. our third equation comes from the fact we had the original constraint. So let's put the constraint up. So what we have to do now is to solve these equations simultaneously. Now, to do that, it's not always possible because, as you know, as the power goes on, solution becomes more and more difficult. There is a factorization for this. These three equations, there's a factorization, which takes a bit of time, but I will skip that. What you can do now is do what I always do, put that into Mathematica. And I just really hope you already finish your assignment because here's the answer. And of course, you get a bunch of points. Okay, that's what 1 over 2, and those are 20 signs. And evaluate them at points. The first line gives you 0.75, the other one is minus 2.5. There's minus 0.25. The top one is maximum, the bottom one is minimum. And that should be pretty clear. And that's what exactly what you get in your parameterized equations when you do that assignment a few weeks ago. So that's the Lagrange multipliers method. It's fantastic. But there's something we have to think about this, right? There's some technicalities. Well, first thing, we assume there is actually extremals. Extrema, okay. Now, secondly, we have to make sure they're both smooth functions. Now, what's that mean? Well, if this condition does not hold, what happens is that we cannot make that geometric argument we made about the intersecting tangentially. In particular, if the gradient of G is equal to 0, okay, if that assumption fails, all right, it's equal to 0, then we'll be dealing with something called abnormal case, or if you think about it, it's a little bit degenerate case. And in that case, you don't know what happens. Lagrange multiplier gives you an answer, but that answer probably doesn't even satisfy the F or the G or things like that. It could be a maximum, could be a minimum, or it could be neither. So you cannot draw a real conclusion from that. And of course, this is a little bit optional, but I should quickly mention this, is that Lagrange multipliers can be used for multiple constraint problems. And this is where Lagrange multipliers really shines. For Lagrange multipliers of multiple constraints, well, we obviously have to consider higher dimensions. And now we have m constraints, whereas before in the assignment we have 1. Now we have n constraints. And each of those constraints is a function, and that is exactly the formulation like that, only in higher dimension. Then we'll still have two criteria. The first criteria is the constraint itself. It should be natural enough because always going to satisfy the constraint. Our second criteria comes from the fact that, well, that's the generalized result from our single constraint problem. Because remember when we talk about single constraint, intersecting tangentially, we make that claim of linear dependency. Now this is a linear dependency provided that all the GKs, all the letter K are non-zero. So here's a generalization of the lower dimensional case. The precise formulation of this is probably beyond what I could do today because there's always a constraint for that. Constraint. Oh, that's funny. Okay, and of course, you calculate the value at each point. You calculate all the points from here. And together, you should realize that we have n plus m equations out of all of this. Now that quickly becomes very difficult to solve because it could be non-linear and a whole bunch of them. Do you really want to sit down for that? So what you do is that you use computational solution, and this is precisely why I used computational solution in the previous question. To illustrate the fact our computational solution absolutely fine. That, but the formulation of those equations are precisely the same. Write down all the constraints and write them as a linear dependent vectors, and you solve them simultaneously. So here we actually conclude our first section on Lagrange multipliers. So let's summarize that. Well, we know that Lagrange multipliers is a method of optimization under constraints. And Lagrange multipliers can be generalized into very high dimensions and multiple constraints. And this is where Lagrange multiplier really becomes the most powerful technique I know so far. And Lagrange multipliers, of course, actually still holds for your degenerate cases, but it's in a slightly formulation, which if you're interested, you can read about it. But essentially what that is, you just put another constant in front of grad G, so that you avoid that zero case. So this ends my first section. So take any questions that you want to strictly ask? Yeah.
Just a question about one of the assumptions. You said that we're assuming that solutions exist. If you can't solve the Lagrange multiplier equations, is that sufficient to tell you that there aren't solutions, or?
Yeah, that could be the case, because if you cannot solve them, perhaps there's something wrong with the equation. Because maybe your solution, your two graphs, F and G, probably don't exist in the same domain, and you could have a problem there. And I actually think of a problem, they actually give you a solution, but that solution is not even a maximum or minimum, because the whole curve is continuous and diverges to infinity and minus infinity, and there's no maximum or minimum. So, yep, great, okay, cool. Let me figure out how to do this. This is IP. So now we'll come to the isoperimetric problems themselves. As I mentioned before, we're representing a theorem here which uses Lagrange multipliers. So what I want to do now is to keep this equation over here, because we'll refer back to it. But in fact, I'll write it smaller. So here we'll give an overview of what's isoperimetric problems. And in particular, we'll actually focus on more examples and applications rather than proofs and derivation, because thanks to Maggie and Kevin, and my life is much easier. Thanks, guys. Yeah. Okay, so isoperimetric problems. The prefix iso comes from the word the same, and perimetric comes from the word perimeter or arc length. Therefore, in the whole topic, you can think of this problem, this IP problem, in optimization of functional under the constraint of another functional, which almost equivalently you can say is under constraint of another integral. So let's define that more precisely. So probably it's good I use the board. So given a function of this form, j of y equals to the integral of x0, x1, integration of some function f, y dash dx. We know how to optimize this. Last week from Kevin, we just simply used the Euler-Lagrange equation on this thing and find an extremal for that. Now once we have this, we can put what we call an isoperimetric constraint. And this constraint is in the form of a functional or integral, and that integral must evaluate to L. So to put that into context, you can think of the constraint as being non-negotiable. Okay? Because whatever function I have, whatever extremal I have, y, it must give me L at the end of the day. If it doesn't, you just throw out that function. It doesn't even, I don't even need that function. So this constraint says that I of y will be between x0, x1, g of x, y, y dash, dx. And that always evaluates to some constant L. Always. So our problem arises naturally is that how do we actually find the extremal for j under this constraint? Any guesses?
Lagrange 45.
You see? You actually just modify the Euler-Lagrange equation, and there's nothing wrong with doing that. As I will actually do the proof of this now. Now, even though I say proof, okay, even though I actually say the word proof, it's not exactly a proof, because the actual proof is really technical, and Kevin already proved that last week. Many of our results are proven last week. So switch. So at this point, I'll actually switch, but then I'll switch back. Okay, make sure that line is correct. Good. So our first step of working towards modifying the solution, the Euler-Lagrange equation, is to, first step, we're going to write y hat. You can think of y as a free variable, and it's made of y plus epsilon 1, eta 1. That's what we had last week, but now we have an extra term here, epsilon 2, eta 2. Now, why do we have this extra term? Well, the reason for that is simple. Later, we're going to substitute y hat into this constraint here. But if we actually do that, we're actually making an assumption that those two functions, eta 2 and eta 1, they both satisfy the constraint. Now that's not the case, because as we see in around step very soon, we'll actually apply the fundamental lemma of first variation. But if we want to apply the fundamental lemma, we run into a problem because fundamental lemma assumes the arbitrary nature of eta 1. So if we actually don't have the eta 2 and epsilon 2, if we just have that, well, the y hat must satisfy this constraint. So eta 1 can no longer to be arbitrary function, and the fundamental lemma does not apply. So perhaps I can do a little diagram to illustrate what's going on. So imagine there's 2-point space. Okay, that's our optimized function, y, and it has the length L. And that's great, that satisfies the constraint. But now, if we just consider, y plus epsilon 1 eta 1, now this function here does not always give you L, does not always satisfy the constraint. Because as you can see, even though they have same endpoints, the length of that is much longer than the extremal. And since the extremal equals to L, the new function you have here cannot be equal to that length. So to counteract that problem, we give that, we introduce epsilon 2 eta 2. What it does is this, is that it corrects, okay, it still has some resemblance, of course. But here we have y hat equals to y plus epsilon 1 eta 1 to eta 2. That will give you L. So what's really going on is this. Imagine that eta 1 and eta 2 are having a conversation. And eta 2 says to eta 1, right? Just be whatever you want, whatever. Whatever your mess, you overshoot, you undershoot, whatever, right? I'm going to clean up your mess. I'm going to make sure overall we will satisfy the constraint. Overall, we're going to satisfy this L. So you can think of eta 2 as being a correction term. It corrects the error estimate or underestimate of eta 1. So eta 1 retains its arbitrary nature. Let's switch back. Look like my mom, because she also clean up after me. Okay, so once you have that, of course, you can substitute those, you can substitute y hat into j and I. Now once you have those two, you have this horrible integral, but don't worry, we don't care about that, because we can consider the whole integral as a function taking epsilon 1, epsilon 2 as parameters. And the same thing happened for I of y hat. That equals some function capital phi, taking epsilon 1, epsilon 2 as its parameters, and that always evaluates to L. So let's take a moment and think. Our problem of optimizing a functional under the constraint of another functional is now reduced to optimization of this function under the constraint of this function. So we happen to just done Lagrange multipliers before. So our equation is applied simply like that. We want to optimize this, so we'll take a graph of this, times some constant lambda, the graph of all of that. Of course, when you apply the graph operator, or del operator, sorry, the del operator on capital 5 minus L, of course, L goes to 0. So you essentially have this formulation. So that's great, because now we're going to evaluate this thing. That's terrifically wonderful and difficult to evaluate that. But Kevin did that last week. So I'm going to quote this result. And the result simply goes like this. That this is result from last week. You evaluate the partial, evaluate at the point epsilon equal to 0. which means epsilon 1 equals 0, epsilon 2 equals 0, because when you have that, you actually have to get the extremal. Now that equals to that equation there. And if you do the same thing with the function capital Phi, you get this integral. Now notice that last week we stopped here. Okay, up to this point we stop here and claim this equal to 0. And you can probably see that already. That this is the Euler-Lagrange equation for just function f. And here we have the Euler-Lagrange equation for function g. But this is the last week, okay? So we actually go a little bit further this time. What we have now is that we're going to substitute these two functions, these two results, sorry, into our original Lagrange multipliers equation. And you get this horrible expression, but the good thing is that we can apply the fundamental lemma now, because this eta 1 that went out is now an arbitrary function. So applying the lemma is perfectly fine. And of course, when you apply the lemma, what's inside the braces goes to the 0. Okay, it becomes 0. And yes, that's a horrible expression to write out again, but we can succinctly write that in this form. Okay, so that's essentially the Euler-Lagrange equation applied on some function, capital F, where capital F is simply little f minus lambda g. So this is actually the second theorem I have today. And this summarized what we've done. And the sum, yeah, there you go. It says that if you want to optimize J of I under the constraint of Iy equals L, then the Euler-Lagrange equation applies on some function capital F, where capital F is simply the integrand of J minus some constant lambda times G, which is the integral of Iy. So let's put that up. Partial F, partial Y hat, minus partial F, partial Y equals 0. And where the function capital F is little f minus lambda g. So this is why that I didn't do a rigorous proof at this point. I only sketched the proof. It's because here is the Euler-Lagrange equation applied on both f and g. So essentially, if I'm going to write this out, it will take a long time, but essentially, I've been doing the same proof that Kevin did last week twice. So there's no much insight of what's going on. But this is good enough for us, because now we can use this to solve a problem. So here's what the audience participation does. So now we have the Didot's problem, and it simply says that if we have a fixed length of rope, what is the shape of the function that maximizes its enclosed area? Anybody have a guess?
A circle?
Yeah, I asked a lot of people about that question during the week. All of them say circle, but none of them actually tell me or justify their claim. So now, I'm going to prove this now. And you can probably show this to someone in your party next week. If you talk about master values, maybe that's what you should do. So just by looking at the question, we know that Jy is the thing we want to optimize. So just by looking at the question, area has to be area.
Just a question,
Yeah.
Are you looking at the closed route?
Enclosed curve. It's an enclosed curve. In this case, it's going to be 2-dimensional. Okay, I should mention that. It's 2-dimensional because higher dimension, I don't know what's going on. No. Okay, don't see that. Okay, sorry. So I of y is our isoperimetric constraint, which is the rod of fixed length. Fixed, iso, length, perimetric. So you see the resemblance here already. This is the isoperimetric problem. And of course, we can actually simplify the problem a little bit. And this is actually the original Didot's problem in, I don't know how many BC ago. So here, we've actually switched back to the visualizer and should do this wonderful problem. Like that. So here's a diagram I prepared earlier because I can't draw. Let's just remove that. Okay, Didot's problem. And what I've done here is to simplify the problem a little bit. What I have here is that, well, whatever length of rope you give me, I can rescale that between the unit, between -1 and 1. And I can probably cut my curve into half, and I will only consider the top half. And this function, let's call that y, has an enclosed area between the function and the line segment between -1 and 1. And the perimeter, if you give me that, that's going to be L. Now, one thing I should mention really quickly is that L should be greater than 0, greater than 2, for the reason that if it's actually equal to 2, then -1 and 1, that's just a geodesic. There's nothing really fun going on. And if it's actually less than 2, it's actually less than 2, then what happens is that you don't even have a geodesic. You're going to go from -1 here and stop and never reach that point. So that's not an interesting problem. Okay, so it's up to this point. Let's do something fun. Now we established that J of y, what we're trying to maximize, is the area. So let's write down the area for this curve here. Audience participation, anyone? No one? Come on, guys. It's going to be area under the curve because we only have that y. Of course, again, I should really quickly mention the perimeter does not count this -1 to 1 line segment. We don't consider that. So this is our area. And now we have the constraint, I of y, which is between -1 and 1. Now this is our perimeter. And perimeter, essentially, that could be considered as arc length. So here is why I'm going to put my arc length formula. And it's just y dash square dx equals to arc length. That's great. We have formulated J and I. Okay? So now we actually want to apply our theorem. And our theorem says the capital F that we're going to be applying on is little f minus little g. Now little f is that, and little g is that. So capital F equals to little f minus lambda g. We would get y, okay, that's f, minus lambda, it's a constant, and g is simply the integral of phi. So this is what I have. And here, here's where I would like to apply the Euler-Lagrange equation onto capital F. If I apply that, this is the result you should get. It should be lambda, sorry. Lambda over square root of 1 plus y dash square plus y plus c1, where c1 is some constant, integration constant in fact. So this is about applying the EL equation on the function f. This is what it is. Now this equation is a differential equation. Great. Dana told us how to do that. Anyone have a guess of how to solve this equation? I was expecting participation, guys. So we know that y dash, we can actually separate this. Okay? And when I do this, you will see why I can separate this. Well, I already did. Y plus c1 squared divided by y plus c1. And of course, this is a separable equation. Is that 2? This is a separable equation because I can put this entire thing, which involves only y, onto the left-hand side by division, and I put dx onto the other side. And simply integrating both sides and get a solution there. So if I do that, this is the result. Y plus c1 lambda squared minus y plus c1 squared dy. Okay, so this is the integral I have. Now that's terrible. Let me write on the next page. I have the integral of y plus c1 divided by this lambda squared.
Can you make it down slightly?
Oh, sorry.
Thanks.
Yeah, thanks, guys. Okay, this is what I had exactly before. I just write it on the next page because already something new. Now here we want to solve this equation on the left-hand side, and to do that we make a substitution. Y plus c1 equals lambda cos theta. And if I use this substitution, the left-hand side becomes, well, y plus c1, okay, set that in, lambda cos theta, divided by, the bottom line is lambda square minus lambda square cos square theta. So by the trigonometry identity, this is going to be square root of lambda square sin square theta times minus lambda sin theta is theta. The right hand side is really simple, right? Because that's x plus c2. Okay, so of course you can see that there's cancellation going on here. Lambda sin theta cancels out with denominator there, and you simply put the minus lambda out. The left hand side becomes the integral of cos theta d theta x plus c2. So of course we all know how to do this, right? Minus lambda sin theta. Now here's an interesting point, is that the author actually did this wrong. I don't know what happened, but that's what actually bugged me for a whole week. He actually did this wrong. Anyway, once I have that, we can actually write this to parameterize equation again onto the next page, because we'll actually be doing something really cool now. X plus c2 equals to minus lambda sin theta. Sorry, y plus c1 equals to lambda cos theta. So now what we want to do is to eliminate theta out of these two equations. And the most natural way to do that is this: x plus c2 square plus y plus c1 square equals to lambda square times by cos square theta sin square theta. So that goes to 0, so the right hand side will have lambda square. So lo and behold, we have an equation for a circle. So now, essentially, you proved if you have that, if you have this diagram, between minus 1 and 1, the maximum area is going to be the arc of a circle. It's of a circle, but what circle? I mean, we're mathematicians, we're not satisfied with the answer, a circle. We want to actually find out exactly what is that circle. So to actually do that, we have to solve the constant C1, C2, and lambda. And to actually do that, or at least get an idea how to do that, wait, let me just, it's a little bit hard to position this. We'll substitute these two equations into our isoperimetric arc length equation we had before. And if I do that substitution, I claim L equals to 2 times lambda times theta. Okay. Now that's a really straightforward integration that if you're interested, of course you can try to do it at home. And now let's see what else we have. Now what we need now is the boundary condition. What I mean by boundary condition is that at x equals minus 1 and 1, y has a value of 0. So that's my boundary condition. So it's bound condition is y minus 1 equals to y1 equal to 0. Now once we have this boundary condition, what we could do is do substitute these boundary conditions into the equation of the circle. And if you do that substitution, you see that C2 equal to 0, and in particular, 1 plus C1 squared equals to lambda squared. Now, of course, that fits with our picture here, because if it's a circle, it's symmetric, and it must be centered around the y-axis. And that's why C2 equal to 0. That tells you it's the x-axis. Sorry, the y-axis. Now, once we have that, we can substitute the boundary condition into these two parameterized equations. If we do that, and in particular I'm going to use this one, it's going to be minus 1 plus C2 equals to minus lambda sin theta, and y is 0 plus C1 equals to lambda cos theta. Now, of course, C2 is 0 as we calculated here, so that's 0. And if we do division of these two lines, you can see that minus 1 over C1 equals to lambda cancel out, so that's going to be 10 theta. Oh, sorry. Yeah, it's a little bit hard to see. Yeah, okay. So once we have this, of course, the negative sign cancel each other out. So we're just simply left with theta equals to the arctan of 1 over C1. So here we have got theta, and this equation here, and what we do now is substitute this back. If you do that substitution, I claim that, well, no claim, you can see that 2 times lambda, but lambda is the square root. Okay, take the square root of both sides times the arctan of 1 C1. And here's why I would like to take a moment and think about this, right? Because now, once I have this equation, if you actually give me an L now, I can substitute L into this, and I can calculate what C1 numerically. And of course, I have to use the numerical method because there's no easy formula for arctan. So once I have that, great, what will happen is this. The equation of a circle, if you just substitute those conditions back, especially that C2 equal to 0, and I rewrite lambda in this way, you will actually get x plus 0. Let me write it again. X squared plus y plus C1 squared equals to 1 plus C1 squared. So, as I mentioned before, if you give me an L now, I can solve C1 numerically. And once I have the numerical solution, I can tell you precisely where is that circle. And that's actually finished our problem, well, almost. Because in actual fact, this is a really nice diagram. It actually shows you that you can, why is this intuitive? You have this, what?
You fix a lamp, don't you?
Okay, I just stand here. You can imagine that I can move this arc up and down. And if C1 actually coincides with the origin, then we'll actually get the semi-unit circle. And once we get C1 equals to 0 and you get a semi-unit circle, then you can perhaps make a symmetry argument and say, well, what's above that is a maximum, because I've just shown that. What's below that, because it's symmetric, you can actually make that same claim that that's going to be maximum if it's reflected. So overall, you can sort of make that symmetry argument that this is going to be the maximum area. Now, of course, that's a little bit dodgy, because I don't know if my solution is a maximum or minimum. But let's just summarize that. Summarize show and tell, right? Yeah. Sorry, show and here. So let's summarize what we did first, and then we'll look at the maximum problem. So here's our solution. We'll actually write down a function capital F first, and then we'll apply the order Lagrange equation to get an ordinary differential equation. And then we'll solve that differential equation, and then we'll solve the constants. So this is the 4 steps. That's all our solution is about, doing these 4 steps, and then understand what is the constant. And here's our conclusion written out nicely in LaTeX. Not LaTeX. So here, I mentioned before that I don't know if my circle is a maximum or minimum or some other critical points, but hopefully I can convince you with this rank of diagrams. Now, all of these diagrams, or the shapes, they are ranked in their the length area ratio. By that, I mean circle has the maximum among all of those shapes, most common shapes you have in real life.
Common?
That's a little bit lollipop, isn't it? So hopefully I can at least convince you that circle is not a minimum among all of our common shapes in life. But of course, to address that more precisely, perhaps that's where the second variations come from. Now, the isoperimetric inequality, which is definitely known in your book, I mean in the Van Brunt group, is that you have this extraordinary equation that if L is the parameter of your curve and A is the area of that, this equation always holds in 2 dimensions. And that's quite cool. And this is just for Daniel, because he was asking about catenary problem last week. And I just put it here and show that this is actually the solution. Of course, that's really messy, but the idea of actually proving the claim is exactly the same as in the Didos problem. You form what's the capital F function, and then you apply the Euler-Lagrange equation. Once you did that, you solve the ordinary differential equation, and you just get a constant at the end. You solve the constant at the end. And of course, this has solution, but that could be very difficult to calculate. So again, computational solution comes in. And you can probably notice that that's exactly what Will had before, is that you cannot make the claim that this C, Greek letter C, if that's 0, of course this one holds, but that will be a meaningless problem because L equals 0. So here we have this problem here, and now I'm trying to relate this back to Lagrange multipliers. So I'm almost finished last slide, sorry. What's lambda? Now lambda, as I mentioned before, is called the Lagrange multiplier, is the actual constant itself. Now if you think about constants, and this is what I struggle with during my research of the topic, is that I would think about lambda as some sort of mathematical constant that actually is there to make your equation work, or some sort of physical constant, as that way seeing the Didot's problem, it actually has physical meaning. But the Lagrange multipliers goes a little bit deeper than that. Now if you actually have fixed boundary conditions, this equation always holds. If you take a partial of J with respect to partial of L, this equation will always hold. And that equals to the Lagrange multiplier. And that, I think, is probably surprising for me while I was doing this, because I didn't know that what's the actual meaning of the constant lambda. And of course, I just have to quickly mention that the techniques we use today in the Didot's problem can actually be applied and generalized into higher dimensions or higher derivatives or multiple isometric constraints. Of course, that is what Maggie covered last week about using Lagrange multipliers in higher dimensions and higher order derivatives. And you do exactly the same thing, and the function you're going to apply on is actually this capital F again. And of course, there's more complication. So here, I actually finished my talk, and the concluding remark is that Lagrange multipliers, optimization under constraints, and it's useful, cool, and helps with assignment. One thing that I should have probably gloss over is that this is not going to be the last time you're going to see Lagrange multipliers in your life, in your mathematical career. That is probably going to pop up somewhere in your life later. And of course, you know, the Euler Lagrange equation for IP, which is this. That's a cool equation. And the Didot's problems, show that to your friend next time you meet party. And you have to interpret the constants in this physical setting. So yeah, here's ends my talk. Thank you.